Whoa, I'm not. Okay, you ready? We see your screen. Perfect. You can start now. Yes.
All right, so today I'm going to present to you the problem number 8, heavy parachute. And just a sec. Yeah, so firstly, I wanted to discuss the problem statement. So the question 1 is it possible to build a magnetic parachute to protect a load from impact when landing on a non-magnetic surface, as you can see on the video right now? And then question 2 is how should it be built to minimize the impact damage? And the third question is what are the limitations of the parachute? And here you can see the approach. So we construct theory, make measurements and the conclusions, and then we try to improve our setup and then discuss the limitations in the end. All right, so to start, I want to talk about the nature of repulsion. So first of all, it's a Faraday law, which is stated as such, as you can see on the screen, where epsilon stands for the electromotive force, and phi b is a magnetic flux that is given by the integral over the area. And the next point is the Lenz law, which is simplified states that the nature avoids flux changes. And from this, we can draw following conclusions. So we get a current flow inside of the metal plate as the magnet is approaching. Induced current is called an eddy current. And flowing currents induce a magnetic field of its own, which push away the aforementioned falling magnet. So first of all, let's visualize the magnetic field of the of our magnet. I decided to concentrate on cylindrical magnets due to the symmetry and Wesley availability. So on the left, you can see the theoretical model of such a field, and then on the right, the representation of the same field using the magnetic paper. All right, so at the time where the magnet is suspended, there is no magnetic flux changes, and thus no magnetic currents, no eddy currents are observed. However, if we let go of the magnet, it starts falling, of course, and then the changes in magnetic flux produce the aforementioned eddy currents in the plate, which produces the magnetic field of its own that is directed in the opposite direction of the magnetic field of the magnet, and thus it repels the magnet. All right, so to summarize it a little bit, here you can see the equations. So the main equations are the gravity and the z direction of the repulsion, which can be calculated as such. And then we can set the magnetic field and, oh, I'm sorry, not magnetic fields, but rather we can use the EMF to calculate the velocity. And using the velocity, we can calculate the current, which we set in this equation. And then, as you can see, it's a quite a complicated equation. And not only being complicated, it is also a part of a differential equation you can see above. That's why the calculation for this is best to leave for the simulations. Yeah, so going up to experimental setup, here you can see I've built a pyramid out of Legos, and then I also cushioned the plate using the bubble wrap to prevent destruction of a magnet. And there you can see the video of what's going on. Yeah, and then let's briefly discuss the pros and cons of setup. So the height is easily adjustable, of course. The setup is also repeatable due to the construction, and the release mechanism, which was done using another smaller magnet, is also quite efficient. However, harder falls may destroy magnets, as you can see on the right. And then faster falls also mean that the less frames can be captured. I used slow-mo footage on my phone, which outputs 240 frames per second, but as we will see in a second, it was not enough. So concerning the measurements that I've done, I've measured time of light and then impact velocity. And I variated following parameters. So first of all, it was magnet type. As you can see, there are different magnets with different pull forces, as well as plate types, as you can see here on the right. So it's different plate material, as well as different thickness and width, and also the initial height. Yeah, so for analysis, I used Tracker to analyze frames and then plotted using the Python. And I also did more than one measurement per each setup to avoid errors. So here you can see the falling time or the trajectory against the time with different setups. And the orange one is the one without a plate at all. So you can definitely see that the presence of a plate does make a difference. However, due to such big errors, given the setup I had, the influence of each and every plate is practically indistinguishable of one of each other. Yeah, and so here it is summarized once again. It's a little bit easier to see in such a manner, and as you can see, also the errors are quite high. So the further things that I variated was height and magnet types, as already said, and you can see that in best case scenario, the slowing down was about 10% in both cases. Which is quite low, as you might imagine. So to the errors, I would say that the upper magnet attraction from the release mechanism might have played a role, as well as the thick cushion of a plate was also preventing to analyze the last 2 millimeters or so of the setup, as well as frames sometimes were non-equal in length by some type of 10% or something like this. Thickness of tracking point, as you can see, was also not infinitely small. And also you can see the this was the same setup, but different experiments. So the same experiments, but I mean, like I tried once, twice, and so on. And as you can see, it interchanges quite high. And so, yeah, the random errors were that first and last frame selection was not easy, as well as point mass selection, as mentioned earlier, and then the side bending of the magnet, as you might have seen from the video. So to conclude, is it possible? Well, it is possible to build a heavy parachute out of magnets and a metal sheet, but significant results can only be achieved using the optimizations, which we'll discuss next. So there is another type of experiment that can be done. It's an indirect type, but it's it provides more of a precision. So we attach magnet to a drill and start spinning it in this direction. And once we approach the plate, it starts inducing the same type of eddy currents, and then we can make qualitative claims about the different materials. With green, I marked the ones that worked better, and then with red that worked worse. All right, but I'd like to propose a reimagination of a setup, and to propose this falling magnet in a pipe. The plate influences are only short term. However, the falling magnet in a pipe uses a constant influence. And as you can see, the magnet reaches terminal velocity quite quickly, and the magnet field is practically time independent. And so you can see here these values I have found from the paper, and there are the average velocities are quite low, which is great for the purposes. And as well, as well as doing that, the experiments, we can also simulate the falling magnet in a pipe using COMSOL, and these results are what we get. As you can see, also the convergence is really high. And finally, to summarize everything, I have compared different setups with each other. So I also looked at the regular parachute just because it's very important as the exercise states to make decisions on whether it will protect the load or not. And yeah, if opponent is interested, we can discuss this more during the discussion. And to give you an outlook, this is everything we have done, and we would like to do this in the future. Yeah, thank you for your attention.
Thank you very much.
Thank you.
Yes,
So, hi everyone, and thanks for the German team because it was very interesting.
please. Yes.
So, the statement of the subject was: is it possible to build a magnetic parachute to protect the load from impact? And it was really well studied by the team, by the German team, and they also studied if you can change the shape of the setup in order to minimize the impact. And they, I think, they also, in some sense, understand the limitation of the parachute. So for the good point, I think there are a good general theoretical understanding, even like the length law, even if some details are missing, and they have a good understanding of the limitation of the setup. They try to vary the magnet weight and also the magnetic field of the magnet, although it was not clear if they precisely measure the magnetic field. They also decided to vary conductivity and also the thickness of their non-magnetic plane. So it's a very good point because conductivity and thickness are two key parameters in the problem. And also they were very clear with the error bar. So even if they are quite high, so they cannot conclude not so many things. I think it was very great, so we understand what are the limitations of the result. So what can they improve? So maybe they could have tried to change the magnetic shape because it's the surface of the magnet that is coming into contact with the copper are very important in the problem. I think that do not really compare theory and experiment. And the very big problem is that they have high uncertainty of they do not have a high speed camera, and so they miss completely the effect because in fact the magnet stop before landing on the copper. That means it reached zero velocity before landing on the copper. And I think it's due to the limitation of the setup, so we can maybe discuss it if they want. But that was the main physics, and this physics also depends on the. You have after some. So I think we can talk about the experimental setup because without a good camera, they could not see the phenomenon. So they just see maybe an average velocity at the end because this phenomenon is very localized near the copper. And maybe what we can talk about also is the parallelism of the if they check the parallelism of the magnet when it falls on the copper plate, because the distance between the magnet and the copper is very important because, as I said, it's a very short range effect. Maybe you can discuss the height of the fall because we have contradictory results with at high height. If the magnet falls perfectly parallel to the copper plate, it can work. Maybe we can talk about varying some other parameter like the copper temperature. You can vary maybe more easily the conductivity. That's the key. That is a key parameter. And maybe we can talk about the interesting physics that in fact the magnet stops if you record it with a sufficiently high speed camera. So.
Great, thank you very much. We can move on to the next part of the discussion between two of you.
All right, thank you for your remarks. It's great that the presentation was perceived such good, so good. But do you mind going back to the pluses and minuses first, that I can quickly comment on that part before going to the discussion?
Yes, after, okay.
Great, thank you. So I didn't quite get what you mean with the height of a fall, but I did variations on that part. And if you were referring to me not increasing the height of a fall further, it was due to the fact that at the heights I did the experiment, it was I almost didn't see any changes of the time the magnet should be falling. That's why I didn't increase it further.
Yeah, it's because, as I said, you do not have a sufficiently high-speed camera. If you want, I can show my result, but only if you want, because you missed entirely the physics, because you cannot record the phenomena really near the copper, and it's like a 0.1 second phenomena, and you see many things, and you cannot, for example, the velocity which is 0 before increasing again. And with your setup, you are limited, so you can only measure the average velocity at the end, and you see it decrease a bit. So if you want, I can show you some results we can talk about.
Well, first of all, thank you for your proposal, but I don't think you are allowed to use your results in discussion.
Because
but maybe afterwards it would be nice. But anyway, I definitely agree that the camera was the main limitation of the phenomenon of the inspection of the phenomenon. But I sadly was not. I sadly could not use any other camera. So yeah, that's.
Sorry, can I ask the chairman to show the result, because they are in clear contradiction of what they observed?
Excuse me. What?
Well, you didn't see, you didn't see the phenomenon. You see that you just see a very slow deceleration, but in fact it's completely wrong, and your magnet will reach 0 velocity before falling down again to the copper. But if you can discuss about it, because there is.
What do you mean?
The physics.
I'm sorry, but
maybe it could be easier if I just show my slide. And can,
do member of jury wants to see what the opponent wants to show us? Some contradicting experiment? Like, if there is interest from member of jury,
why not?
It's not contradicting rules. You have right for commentless short.
Okay.
Commentless short demonstration.
Okay. At 0 here is a copper plate.
Commentless short demonstration.
Yeah. Yes. And just to say that if you just track with a high precision camera, the magnet will effectively slow down a lot, and in fact it will in this area here.
No, it doesn't fit what's called commentless short demonstration. Commentless short demonstration is when you, for example, can you finish? Thank you. When you, for example, have some video of the phenomena which contradicts the reporter theory, you can say nothing, show this video, and it's only scenario when opponents can present any kind of their own work. If you have such stuff, we can like make it. If you show in any other kind of materials, it's not allowed. Does it make sense?
Let's go maybe to other points of criticism, because time is running out. So just let me quickly show you. Like, first of all, there were a few things I did not discuss, and one of them was that I have tried another setup to decrease the load in the magnet, and like I attached masses on this side to effectively reduce the acceleration, but sadly it didn't help that much because of the friction and this wobbling of a magnet. So as you can see here, it lands much smoother, and I didn't even need to slow down the video, but sadly it does not necessarily rely on the phenomenon itself. And then you also said that the shapes of a magnet should be researched further. Well, I agree, but not the cylindrical shape themselves, but the arrangements of the magnets. What I mean by that is the Holbach array. It's such array that allows almost 100% magnetic flow on the one side of the magnet, while while the other side is completely empty, or more or less completely empty, which would increase the efficiency. But as I have spectated from
so we can just I have the video. Can I just show you the video, and after we can maybe talk about it?
If that's not allowed, then sure, go ahead.
Don't you want to listen to the report? Okay. Okay. Meanwhile, like, it's time for general discussion already started.
Yeah.
Okay, we can watch your comment test video.
So yeah,
your comment list video.
Okay, it's
Comment test. Okay. Et maintenant tu quittes et tu reviens sur ce qui.
Well,
we can watch it. Thank you.
Thanks for showing it. Definitely shows the flaws of my setup. From what I've seen, I definitely agree that the magnet is reaching a zero velocity before hitting the ground. However, what I did notice conducting my setups, that the magnets were oftentimes chipping, so they were broken after the fall, and that to me signalizes that even though my setup may not be perfect and the velocities I've measured may also not be perfect, the one bottom line that there is to see is that it's not an efficient parachute in this case and form. That's why I proposed a different
but maybe what was the magnetic field produced by your magnet? Because the effect depends really on that and on the thickness of the copper plate you use. So because the problem is when you increase the magnetic field, you increase also the weight because you add magnet together. So do you know what was I mean the magnetization per volume? Because I think it's the key point here.
Sorry, you mean the?
I think, do you know the magnetization per volume of your magnet? Because maybe your magnet was not strong enough to see this.
Well, I do not know the constant, but it was a neodymium magnet, and I think that's that's the strongest type if we do not go into the cooling of the magnet.
Okay, and also, are you sure that your plate was sufficiently thick? Because I mean, if they were not sufficiently thick, because copper is very important, is a key parameter in this experiment. Maybe it would not have worked if you have not enough thickness.
No, I used a 1 centimeter thick copper plate. Furthermore, I tried to stack the plates on top of each other, which, while may disrupt the eddy currents in some order, but still such a 5 centimeter thick plate should be sufficient enough, I think, to spectate the effect, even if I cannot measure it directly.
I see. And did you check that your magnet follow really, as I said previously, in a parallel manner to your to the copper plate? Because with I mean, with if you have a ball like a spherical magnet, you will not have a problem. But here, I think that the magnetic field is really stronger, like perpendicular to your magnet, and I think if it deviates a bit, you will have the effect greatly reduced. So did you check that? Can you check that on the video? Or?
Yes, I definitely agree with you on this part. And also, I tried like letting it go flat and letting it go on the side, and it was definitely better flat. But the reason it didn't quite work out in my setup, well, I tried a few setups and it wasn't working 100% of the time. I tried cherry picking the falls. As well as tried to impact the landing however I could, but I think, well, maybe you have a proposal on how to improve the setup so that the magnet would land more parallel to the plate.
I don't think you have that. You had that at your home if you had done this at your home, but you can use maybe an electromagnet. And you just stop the current flowing inside the electromagnet, and it can you can have maybe it's more parallel than just with your method, I think.
Well, I agree, but the reason was that I wasn't in possession of an electromagnet.
Yes, it's just if you have that, I think it's
yes, I agree with
Thank
you.
you, everyone. You ran out of the time of all discussions. Dear reporter, now is your time for the concluding remarks.
I definitely think that the opponent helped me to understand the setup better, as well as to understand the limitations of my measurement equipment. And it would be very interesting to me to research this topic further. As well as I'm grateful for the general discussion with the opponent, which was quite fruitful in my eyes. However, I need to say that I'm still not quite convinced that that this setup with a magnet and a plate is the optimal one, because as I've mentioned in my presentation, the forces that are being applied are not constant but are only short term, and that the setup with a falling magnet through a tube is a better option if the load is not too voluminous and can fit through the tube with a magnet. Thank you.
Great, thank you very much.
Yeah, thanks. Well, I want to come back at the statement of the problem where they say that they asked whether it's possible to build this magnetic parachute to protect a load from impact. Maybe a question to both the reporter and the opponent. Practically speaking, do you think this would be a good parachute if we had to put humans in it? Would a human survive such accelerations? So what would you say on that?
All right, I hope opponent does not mind if I start. So I am 100% convinced that it's not the best setup for human transportation, because of so much things. First of all, if we want to have a big setup, then we need to spend a lot of money on metal and on magnets. Second of all, magnets, neodymium ones at least, are really not stable. They chip away easily, which I also seen from my experience for small heights. Third, the interaction is also on only shorter heights, so it would not make sense for a human to be slowed down in 20 centimeters. What I think is the better idea is to use copper tubes, or to use the magnet and the plate for really small loads. For example, in the laboratory, if you need to, I don't know, drop a small vessel of liquid and do not break the glass, maybe for this.
Yeah.
Can I answer too?
Sure, yeah.
See, if we expand our theoretical model to one with a human being, you can have an acceleration of 10g. And so I think you can still live even it's not very comfortable.
Okay, thanks a lot.
Thank you. Georgi, your question?
Okay, thank you. I have a short question, I think, to the reporter. When you model the interaction of the magnet, moving magnet with the plane, how did you model your magnet? Was it a point dipole, or was it a uniformly magnetized cylinder? I missed it somehow.
It was indeed a fully magnetized cylinder. Yes, I did not talk about this in detail, because what I did is I have taken the pre-made, so to say, magnetic field from a paper and just plugged it into my equations.
It's okay. Yeah, thank you.
Thank you. Zahar, we didn't hear you today. Please ask your question.
Okay, thank you. To the reporter, can you show us these plots again with the parabola, which compare the results when you with the free fall and yes.
Mm-hmm.
And the question first to opponent, what kind of problem is with these plots? Do you think they are okay? To the opponent.
To the opponent?
Yes.
Maybe remove this.
I think you miss the interesting area that is near at the end, and you have a large error bar, so you cannot not say anything.
You said that the reporter did not observe the correct effect, that
yes.
he explained his experiments in an incorrect way.
Yes, because
so is it seen from these plots, from these curves?
Yes, yes, because you see at the end he has not enough point to clearly see the phenomenon. I think so. I think he just measured an average velocity, and not the full effect.
Okay, thank you.
Thank you.
Maybe a reporter can also comment on this.
Yes, I definitely agree. The large error bars come from the mainly from the amount of frames per second my camera was able to produce, and this is of course why I do not see the flattening of the curve towards the end. The flattening you see here is mostly towards the mostly because it was maybe the last frame where the magnet was hitting the plate already, so that's why it is happening. I agree.
Thank you. Also, Alexander,
okay,
your question.
Okay, I think the players will answer briefly. Could you please imagine why you haven't obtained the such slowdown as the guys from YouTube did? And the first question, the first answer I want to hear from the opponent and then from the reporter, please. And please be brief, because we're running out of time.
I think it didn't choose a strong enough magnet.
And that's enough. Yeah, thank you. And what the reporter will say?
Yeah, it definitely can be the case because on YouTube we've seen the larger magnets.
So as the magnet, the huge magnet will be enough. Yep.
Yes.
Okay. Thank you.
Thank you. It's perfect how we fit the time. So now.